right, welcome everyone, and thank you for joining us today. My name is Angela. I'd like to welcome you to our webinar titled Improving Speed, Efficiency, and Resilience in the Development of Biopharmaceuticals with End-to-End Bioprocess Digital Twins. Before we get started, I just want to go over a few logistical details with you. So this is what the 23 webinar platform should look like on your end, with the screen on the left-hand side where you're currently seeing the presentation, and on the right-hand side here, you should see the questions panel at the top.
So there's an equation-based approach, which means that you can customize the models without actually requiring any programming experience. And this is really great if you want to be implementing a few kind of tweaks to the model based upon something you've read in a paper or what have you. The other thing to comment on, I suppose, is the underlying technology, the algorithms which we have here. So GPROMS has now been around, I think, for sort of like 25 years, and there's a big team of people, developers, that are working on the software continuously. So the underlying algorithms tend to enable faster calculation. So we have global algorithms for things like validation, optimization, and GSA, global analysis. So we can parallelize and we can utilize high performance computing. And also the software includes a number of capabilities that are not typically available in other tools. So there's this variance-based global sensitivity analysis, there's the design space explorer, which we showed a bit of, there's surrogate modeling, the state estimation, which we talked about, and then of course the nonlinear model predictive control capabilities. So I think that's the other big difference. So the GPROMS digital applications platform provides this very proven, robust solution for online deployment, which has already been used for many customer case studies. Okay, so I have another question. So this is a bit more related to the online. So could you elaborate on the interoperability between GPROMS and DCS systems like Delta V and Pi Server for data integration? So so this is a great question, because so with these tools, integration is possible with any existing automation system that you might have. So it doesn't have to be Siemens. So it can communicate via things like OPC UA or any other kind of Ethernet-based communication protocol that's common in OT environments. So the GDAP tool, which we discussed, has an external data manager. It manages communication with the external data servers, such as control systems or data historians, SQL databases, etc., etc. So this can be used to integrate with offline, near real-time and equipment data as required. Okay, let's pick another one. So can you integrate with other tools, such as Python, MATLAB? So yeah, we hear this very often, so yes. So what we have is we have interfaces to both Python and MATLAB. We also have a general interface that allows you to connect with other tools, other software. So there's a dedicated interface to Python called Adapter-FO. This lets GPROMS call Python scripts, so you can actually run Python from inside GPROMS. And this is very useful often if you have a Python model for sort of part of the bioprocess. So a good example here is using a Python script to calculate a parameter for a unit operation. And you wanted to use this because you developed a statistical model for that outside of GPROMS. So something like KLA is a good example, where you might have a Python model that's able to calculate KLA from a number of different equipment geometries or RPM or what have you. And then there's another tool, it's called GoPython, and so you can actually call GPROMS from Python itself, and then GPROMS will then send specified outputs, so basically results from the simulations back to Python. So yeah. Okay. There's one here on the end-to-end. So how does GPROMS deal with scheduling in an integrated model? So there are lots of approaches actually for scheduling. Now, the recommended and the simplest approach to model the scheduling of sort of batch bioprocesses or even continuous, I suppose. So when you start up or when you shut down continuous processes, is using the bioprocessing model library. So within the model libraries, there are things like tanks and control system models. And within those models, indeed actually within the bioreactor and the chromatography and the membranes and what have you, there's an inbuilt scheduling options for each of the unit operation model. And really what's underpinning it, there are equations in each of the unit operation models that sort of automatically activate and deactivate as a function of time, or there's some type of trigger variable defined. So for example, you could have a trigger variable, which is like the volume in a tank. So the tank starts to discharge once the volume exceeds a certain value. The other thing, I suppose, is that the model libraries also include these control system models, which can be coupled with sensors and sources. So, if you have a control system for something like DO or for pH, then you can implement that control system, and the sensors and the controllers will be able to simulate that control system as if it was the real control system. And then there's also a much more advanced scheduling tool within GPROMs where you can define very detailed operating procedures. So sort of the recipes that defines periods of operation. Okay, great questions. So I've got one bit simpler. How long does it take models to solve? So a single simulation usually ranges from seconds to minutes, something like that. So when you do large parameter estimations, what we're doing here is we're iteratively solving many simulations in order to kind of decide or work out what parameter value minimizes the difference between the experimental data and the model predictions. And so these calculations are more complex. They might take something even up to several hours for something like a bioreactor, which has lots of experiments, lots of data. It's similar with global system analysis. If you're performing hundreds or even thousands of individual simulations. Now, one thing is that GPROMS comes with this built-in parallelization. So with the calculations, you can decrease the time it takes to do those calculations proportionally to the number of cores that you have in your machine. And you can send this to high performance computing clusters or even to something like Amazon Web Services to really speed up those calculations if desired. When you take things online, I think because bioprocesses often take lots of time, like hours to days to perform, the calculations can usually be performed well within the desired time frame. So that's not really ever a worry. Now, what we can do though is if models become too complex to solve quickly and reliably online, we have a tool in GPROMS to generate surrogate models. So we can generate things like PLS or ANN models based upon a detailed mechanistic model, and the ANN is able to solve much quicker and more robustly. Now, we don't use it for bioprocessing very often. We don't need to, but it can be useful. We often use it when we're kind of simultaneously modeling multiple manufacturing facilities in the energy and chemical sectors, for example. Okay, what's the time? Okay, we've still got a few minutes, which is great. There's a few more questions here. So, is it possible to build purely statistical models within GPROM software? Yeah, so it's possible. So you can do statistical modeling in GPROMs, but to be honest with you, there's usually better external tools, Python or other tools, and they're normally better because they're entirely focused on statistical modeling. So because GPROMs is more of mechanistic and hybrid process models rather than statistical models, actually probably the best way and what we make sure to offer is there are definitely good ways to connect statistical models to GPROMs models rather than try and reinvent the wheel, so to speak. Okay, there's another question on models here. Does GPROMS contain CFD models? No, so it's a good question. So GPROMS doesn't contain CFD. So GPROMS is really process models. Siemens has other software for CFD, Star CCM Plus, for example. Now, one thing though is that the real advantage of CFD is that CFD is very good at predicting fluid dynamics as a function of the geometry of a bioreactor or something like which is very irregular, like the shape of a stirring impeller, for example. And what you can do is actually you can connect GPROMs to the CFD model. And you can do this two ways. You can either do it by generating something called a reduced order model or a surrogate model from the CFD, and then you can link that to the GPROMs variable. KLA is a good example here. Or we can also do something called multi-zonal modeling in GPROMs, where we break up the unit operation into multiple zones in GPROMs. And so each of the zones then has its own mixing characteristics and the concentrations of the various species. And then what we do is we can use the CFD to determine the flow of material between the zones in the GPROMs model. So obviously CFD is quite computationally heavy. So typically what we do is we run CFD in advance and then we kind of import that into GPROMs. But it is also possible to do a two-way connection where GPROMs is then able to send information on the zone back to the CFD, so it could change the viscosity or something, which would then update the CFD. But of course, that's more definitely for R&D, where there's more time available. You don't need to solve these models so quickly because the CFD will really slow down the calculation. Okay. Okay, very general question, which is very hard to answer, but how much data is required to calibrate these models? So with the software, it comes with guidance documentation for each unit operation model on the kind of general data requirements for model calibration, also sort of how to use the data. So in general, the data required to calibrate is always less than kind of an equivalent data-driven or statistical model. Now there's lots of factors that comes into play, right? Because it could be prior knowledge that reduces the data required, the model complexity. If you have a more complex model, you want it to predict more factors and responses, you need more data. The context of use is important. What kind of questions are we expecting the model to be able to answer? So the exact experimental data required depends on lots of factors. We need dynamic data most often. This is a big difference between statistical modeling and process modeling using these dynamic mechanistic models. So you've seen in the case studies that we're taking samples at regular intervals. Typically, our customers utilize process development data from scale down lab experiments, and then they're able to transfer parameters to models of larger scale because many of the parameters in these mechanistic models are scale independent. So you only need to really re-estimate or tune the scale dependent parameters, which also reduces data requirements. And yeah, maybe just generally, for chromatography, you've seen it could be as low as 3 experiments. For bioreactors, you've seen today how sort of you can get a fairly reasonable prediction using something like 10 experiments, covering quite a wide range of conditions. We have another question, which is about sort of how many inputs and outputs are we considering. So with a bioreactor model, you typically are going to be considering maybe up to sort of like 15 different species when it comes to these models. You might also consider temperature shifts. You might consider the initial seeding density. So you can tend to have quite a large number of factors, and it means the models you might have something like 20, 30 different parameters that we need to estimate. Okay, and then for something like a TFF or a UFDF, you could have something like 10 experiments to calibrate your model. Okay, all right, so a couple last questions. I know we've got like only a few minutes. So do your models consider molecular structure? So in general, no. We've implemented models that don't consider the molecule structure. So you do need to calibrate the models per molecule. We are finding, though, that models can sometimes be similar between molecules, especially if you've got the same cell line, for example. So this opens that possibility to build these platform models where you have a base structure and then you tweak those models for each new asset. For some of the absorption isotherms in chromatography, you've got charge, which is related to molecular structure. For TFF, there's a model you have which predicts the effect of Donan partitioning on the final buffer composition. And of course, like KLA, it's not KLA, sorry, pKa of the molecule is related to amino acid sequencing. That's useful. And then, okay, one last question before we finish up, which is probably the hardest one. Left the worst to last. Can you comment on regulatory considerations when using models in filings? This actually is not so hard. We have good experience on this. So what we recommend is something which is closely aligned with the regulatory guidance on this, and it's also something that we've presented on with the FDA actually a few years ago, and it kind of aligns with the principles of model qualification, verification, and validation. So this is being set out in sort of books and literature on scientific computing. And essentially, what we do is when you want to use something and when you want to file a model, we recommend taking a risk-informed credibility assessment framework to kind of determine how accurate does the model need to be, what's the validation space, before we perform the experiments to calibrate and validate it. And what you need to start with is what's the question the model needs to answer, or what's the concern that's being addressed. This then establishes the role and the scope of the model in addressing that question. And so what you need to do is provide an explanation of how the model or the digital twin will be used to answer the question, and also what are the other sources of evidence that we use as part of that decision. And that really helps, because if you have lots of sources that are informing a decision, it will reduce the importance of the model and the risk of the model. Of course, yeah, risk is a big part of it. So we need to know what's the consequence of making a wrong decision, and what's the severity of an adverse outcome if you have an incorrect decision. So all of this kind of leads into these credibility risk assessment, and there's sort of these 15 categories where you have to justify the equations, you have to provide evidence that they've been implemented correctly in code and that they're being solved accurately. And then last but not least, we need to provide evidence that the model is being calibrated properly. So one of the, obviously the key advantages of using a commercial software like we offer at Siemens is it provides you with assurance that the first two categories are met, and then the model calibration approach is suitable. Okay, so yeah, great question. I think I'll leave it at that and pass it back over to Angela. So
Yeah, thanks, Ed.
thanks very much.
I did just want to address one question that I did see come in a few times about the recording of the webinar. So within the hour, you will receive an email with a link to the recording so you can view the webinar again on your own time. And with that, I just want to say thanks to our presenter, Ed, again, and thanks for everyone for joining today. We will look forward to hearing from you soon. Thanks, everyone.
Thank you for watching. To learn more about this topic, check out the links in the description. And if you enjoyed what you saw, like the video and subscribe to the channel.